Hello friends, in the last video we learned about the welded connection and we have seen what are the different types of weld that we have, what is the welding process itself and how we can calculate the throat thickness of any given weld. And once I know the throat thickness, we can use IS 800 to calculate the weld designer strength. Now in this video, we are going to see what are the different steps that one has to follow for designing any welded connection. So let's get us started. So in general, the welding design process can be divided into four steps. In the first step, we have to assume a weld size. And how we assume a weld size, that is given in the code. So code gives for connecting two plates, if I know the thickness of the plates, basically we can use some guideline. For example, we can find what is the minimum weld size that we can use if the thickness of the plates are known. Similarly, we also know what is the maximum weld size that we can use in such cases. So basically we can try a weld thickness T that lies between T minimum and T maximum, and then we can reiterate and we can come with a optimum or economical weld size. So once I know my weld size, I can calculate the design weld strength, and this is given in the code. So code gives a formula for calculation of weld design strength PDW. So this is basically amount of force that a weld can take, and this is nothing but area of the weld, that is effective area, multiplied by the design weld stress. Now this area is nothing but length of the weld, that is LW, multiplied by the throat thickness, that is TE, and we have to multiply this by a term that is Fwn divided by gamma mw, which is equals to design weld strength, basically a stress, Fwd. Now Fwn is the nominal weld design capacity and gamma mw is partial factor of safety. This term, that is throat thickness, we can also write K times S, where K is a constant that depends upon the angle between the two plates, that is the angle between the fusion faces that is going to be weld, and this S is the weld size. And the nominal weld design stress, that is Fwn, can be written as Fu divided by root 3. So this formula can be used to calculate the weld design strength for any given weld size. Now we can also calculate the design weld strength per unit length, and that is used in the next step for calculation of weld length. So in the second step, we can calculate the weld length. So let's say if I have two plates and one plate is applied a force P, then we can calculate weld length, that is LW is equals to P divided by weld strength per unit length that we calculated in the previous step. So this is P divided by weld strength per unit length. So in next step, we have to account for different kind of reduction factors, if any. For example, if I have a long joint, then we have to add some reduction. If you remember when we were discussing connections and that point of time, bolted connection, at that point of time we said if I have a long joint, that is if joint is long, that this length is long, this plate and this plate is connected and this joint length is long, In that case, the distribution of stresses or distribution of forces on all the bolts are not equal. So these forces are not equal. Basically, they follow some kind of non-linear pattern. So they may be something like this. So to account for this, that is, if I have a longer joint, in that case we have to multiply the designer strength by a factor, and that factor is related to long joint, and there is a reduction factor, and the code gives how we can calculate this reduction factor. And this is given in clause 10.5.7.3. So what is this? So code says the clause 10.5.7.3, this clause is related to long joint, and this says when the length of welded joint, that is this part, if I have one plate is here and another plate is here and this two plate is connected and this length is very large. So when the length of the welded joint Lj of an splice or end connection in a compression or in tension member is greater than 150 times Tt. So if this Lj is greater than 150 times Tt, in that case we have to multiply the belt designer strength by a reduction factor. So the design capacity of belt that is calculated in the previous clause has to be reduced by a factor of P1 BLW. That is this formula 1.2 minus 0.2 Lj divided by 150 times Tt. So now if you see this formula, there are two terms. One is Lj and another is Tt. So what is the meaning of these two terms? That is shown here. So the term Lj is length of the joint, that I already said. So this is the length of joint in the direction of force transfer, and Tt is nothing but throat thickness of the belt. Sometimes it's also written as Te. So throat thickness is Te or Tt, and basically this throat thickness is nothing but equals to K times belt size S, and we know how we can calculate or how we can find the value of constant K that is given in the code. So this means if I have a long joint, I have to reduce my design belt strength, and subsequently we have to calculate the belt length that is designed or that is required for a given load P. Now in the final step, step 4, we have to basically calculate some kinds of aesthetic, and that is, for example, in this case we can calculate the end return and provide, basically end returns are provided at the each end of longitudinal fillet belts. So we can calculate the end return lengths and we have to provide these end returns at the end of longitudinal fillet belt. So these are given in the code, and this is illustrated here. So if I have a plate and this is connected to this gusset plate through welding, so there is welding here, then we have to provide some in return. So this is called in return. So this is extra weld that we have to provide. So this is the length plus this is the length, that is the calculated belt length that we have calculated in step 2. But now apart from this, we have to provide an extra belt length that is called in return. That is, this distance is given in the code and this has to be equals to 2 times S, where S is the belt size. So we have to provide at this end as well as this end a belt length of 2S length. So this summarizes the 4 steps that one has to use while designing a belted connection. Now we will illustrate these 4 steps using an example. So this example says we have a channel section and this is ISMC 300. This means I can see the properties of this section in SP6. And this channel section is used to transmit factored load of 800 kilonewton. So we are trying to apply a force of 800 kilonewton. The channel section is connected to a gusset plate and this thickness of gusset plate is 12 mm. We have to design a fillet belt. If the overlap is limited to 300 mm, so between this connection, that is channel connection, and the gusset plate, the fillet belt length is limited. That maximum we can build up to a size of 300 mm. We will illustrate this using a diagram. So we have force here and this force is 800 kilonewton and this is my channel section, that is ISMC 300, and this is the gusset plate and the thickness of this gusset plate is 12 mm and the maximum limited length is 300 mm. So this is the only overlap that we have and that we can use for welding. This side also we can build up to 300 mm and this depth of the channel section will again be 300 mm because this section is a ISMC 300. So how we will solve this problem? So if you remember the steps, in the first step I have to assume some build size and we will use IS 800 for the initial guideline for the build size. Now once I know the build size, in the next step we can calculate the build designer strength per unit length and then we can divide the total load divided by the build designer strength per unit length to get the build length. Now the maximum build length in this case that we can provide is 300 plus 300 plus 300, that is 900. That is, this will be the situation if I provide all these faces as a builded. Now if my build length is less than 900 then we are fine. If build length required is greater than 900 then we have to look for some different arrangement. So let's first find what is the build length that is required in this case. So this is the properties of ISMC 300 section. So area is given and thickness of flange is given and thickness of web is given. So thickness of web, that is this portion, that is 7.8 mm. So this is perpendicular in this direction. So this thickness is given. Now you see the gusset plate is 12 mm thickness. So this gusset plate is 12 mm and basically when we are going to connect these two, we have to connect this welded part is here, the web part and this gusset plate, and we have to also basically connect this side, in this case the flange side. So we have to consider the minimum thickness. So between this flange portion, web portion and the gusset plate portion, which is the minimum? So thickness of web is the minimum. So we can say TW is the minimum among all the other plates that is getting to be joined or that is getting to be welded. So TW is 7.8 mm and T of gusset plate is 12 mm, and based on this we can go to the clause and we can see. So for this we can go to this clause and that gives me build size, that is minimum build size of 3 mm. And this is given in table 21. So if you see this table 21, this gives you the minimum build length. So if you have a plate up to 10 mm, then minimum size that you have to consider is 3 mm, and that's why we are taking minimum build size of 3 mm. Similarly, we can find the maximum build size, and this is given in clause 10.5.8. So it says where the fillet weld is applied to a square edge of a part, the specified size of the weld should generally be at least 1.5 mm less than the edge thickness in order to avoid washing down of the exposed areas. And this is illustrated in figure 17a. So you see in this case, this maximum thickness that we can use is basically T minus 1.5 mm. So this total thickness is T mm, then this thickness is T minus 1.5 mm. So that's why we are using in this case, because my rolled section has a minimum thickness of 7.8 mm, and then we have to reduce by 1.5 mm. So maximum belt size that I can use in this case is 6.3 mm. So minimum belt size is 3 mm and the maximum belt size is 6.3 mm. So we can use a middle value. So let's take a belt size of 6 mm. We will use this belt size for designing this belted connection. So we can calculate the effective throat thickness, that is K times S. These two angles or these two plates, one is the gusset plate, another is the channel section, are perpendicular to each other, and that's why K factor is 0.7, and we have used a belt size of 6 mm. So belt size multiplied by the constant K is basically effective throat thickness, that is 4.2 mm. Now once I know the throat thickness, we can calculate a strength of belt per mm using this formula. Now we have to consider a Fe410 steel, and this is given, this problem gives the site weld, and for that the partial factor of safety gamma mw, that is 1.5, this is given in the code. So if I consider Fe410 steel, so we can plug all this value in this equation. So Fu is 410 and T effective that we already calculated, if throat thickness is 4.2 mm, and then this is root 3 and gamma mw, that is partial factor of safety for the site weld, is 1.5. So if I plug all this value and calculate, then become a value of 663 Newton per mm. So now I know my belt strength per mm length, then I can calculate what is the belt length that is required in this case. So as I said earlier, the belt length is equals to P, that is the load applied, divided by a strength per mm. Now in this case, we have applied a load of 800 kilonewton and the belt strength per mm is 663. So this gives me the belt length, that is 1207 millimeter. So as I was discussing earlier, the maximum belt length that is available in this case is 2 times 300 plus 300, that is only 900. But the required belt length that is greater than the maximum belt length that is available, then what we do in that case? So what is the extra length? So we can calculate this 1207 that is required minus 900 that is available. So we have to provide an extra belt length somehow, that is 307 mm. So how we can provide this extra length? So this is a question. Now one possibility is, so we have this channel section and then this side the gusset plate. So what we can do is we can make some groove here. So this is one possibility, and then we can do the slot welding. So let's use slot welding for this purpose, or to provide the extra belt length in this case. So code gives us for the maximum slot width that we can use in slot welding, and that is this distance, that has to be minimum of 25 mm or 3 times minimum thickness, that is the plate. So if I have two plates, so what is the minimum thickness of these two plates? So 3 times T minimum or 25, whatever with the minimum value, that is my slot width. So if you see, this minimum thickness is 7.8 mm and this is 3, so multiply it by these two terms and calculate whatever be the minimum. So in this case, this term is 23.4 mm, which is the minimum. So we have to use a slot width of 23.4 mm. So let's round it up. and then we can use a slot of 25 mm. So we are going to use a slot of 25 mm, and what we will do, so we have a gusset plate this side and this side, so there is a gusset plate, and this side also we have the gusset plate. So what we will do is we will weld this portion, and we will also build this portion. Similarly, all this we have to build, and this is the slot width, that is 25 mm. So what are the extra length that we are going to provide? So basically, if I use slot belt, we are going to provide this extra length. So let's call this as X. We are also going to provide this extra length, that is X, this extra length X, and this extra length X. So we are going to build all this part. So in that case, basically we are going to provide some extra length, and this is nothing but 4x. So if you see x 4 times, that is this one, this one, this one, and this one. So we have provided an extra build length of 4x. Mind, we have not provided this length and this length as extra length, because if I have simple this belt, that is this one, if we have no any slot, in that case also we already have provided this. So this is same as this portion. So this portion we cannot consider as an extra length. So this is not an extra length, because this is gone here. So we can equate 4x with the extra length, that is 307, and this gives me value of x, that is 76.75 mm. So let's round it, and then we can provide a belt of 80 mm length, that is x value is 80 mm. So finally, we can design my connection something like this. So we have provided a bed length of 300 mm, this side also 300 mm, and this slot width is 25 mm, this slot width is also 25 mm, and this, let's say we are providing at a distance of 100 mm, and this is also 100 mm. So this is 100 and 100, 200, 225 plus 25 to 50, and then this total length is 300 mm. This means this portion will be 50 mm. So we have a 50 mm length in the middle, and then 300 this side and 300 this side. So if you consider, or if you total, so this will be 300 plus 4 times 80. So what is the total length? So 300 plus this length is 300 plus 4 times, sorry, not 4 times, uh, this length is how much? Yes, 4 times 80. So this length is 80. So this is 4 times 80 plus 300. So we have provided 900 plus 320. So that is basically we have provided a length of 1220 millimeter, and the required build length is 1207 mm. So basically now we are safe, because we have provided little bit of extra build length in this case. So in this video, basically we have seen how we can use 4 steps to design a belted connection. And this we illustrated using an example. In that case, you have to first consider the initial belt length, and then you have to calculate the belt designer strength, and then belt length, and then you have to basically provide this belt length in some way so that you are safe. That is, the belt strength or belt resistance is greater than the load that is provided to this member. In the next video, we will discuss about the belt that is in shear as well as in the tension. So we can stop here, and we will see you in the next video. Thank you.